All right, this should already be in our notes. If it's not, make sure it's there. If it's not completely in the notes, make sure it's completely in the notes. We talked about secant lines and tangent lines, and what the slope of those lines tell us about the function. A secant line is a line that connects two distinct points on our function. You can extend it, it might pass through a third point, but whatever. We're just talking about the 2 points. Tangent line is a line that just touches a function at one point. However, it's a line, you need 2 points on a line. That line is actually created by 2 points infinitely close together. And you connect that really, really small line segment, but extend it, and all of a sudden you see that it's essentially just touching your function at one point. Now the slope of the secant line gives you the average rate of change of the function. So if this slope of this line is 1/2, you would say on average, your function is increasing 1/2 of a y for every 1x to the right between A and B. Between A and B. Sorry for being messy there. On average, f of x is increasing 1/2 of a y for every 1x we're moving to the right between A and B. All right. Well, we don't have to talk about an interval when we talk about the slope of a tangent line. If this slope is, say, 2, we would say exactly at x equals c, the function is increasing 2 units for every x unit. Now you might be thinking, you know, how do you move 1 unit to the right? Well, it's just at that point, that's how quickly I'm moving. Going up 2 units per 1y. We can kind of work that down to, you know, different intervals. Okay? Now, this brings us to what we'll talk about for the rest of this semester, derivatives. What is a derivative? You've probably heard of that word before, but you're unsure of what it means. A derivative is just a fancy math word for instantaneous rate of change. Which means you have 3 terms that all mean the same thing. You need to be comfortable with using all 3. I could ask you about a derivative. Well, you know that's equivalent to asking about the instantaneous rate of change of a function. Well, you also know that's equivalent to the slope of a tangent line. This is vitally important in this class, understanding that all 3 things are the exact same. And I could ask different questions, but they would really be the exact same question. If I ask you for the derivative, if I ask you for the instantaneous rate of change, if I ask you for the slope of the tangent, you would be able to say, okay, that's the same. Now, let's go away from kind of straight line motion, which is what we were talking about last class, and like the exact velocity at a point. And let's just talk about a function and how a function is changing at a specific location. Okay? So let's deal with this function 3x squared minus 2. And let's find the exact value of a derivative at a specific location. Or let's find the instantaneous rate of change of the function at a specific location. Or let's find the slope of the tangent. All three, this, and this, and this, all the same. And let's find it when x is 2. Now, since we have a function, I have an infinite amount of information about where my points are located on my function. Okay? I don't have a table. I'm not just dealing with whole numbers. I'm not dealing with 0, -2, 1, 1, 2, 10. No, I have points that I know are just to the left and just to the right. Okay? Now, you guys with a calculator, talk amongst your neighbors and figure out a way by just using the slope formula that we know that you can find the slope of the tangent to this function 3x squared minus 2 right when x is 2. And see if we can find a value, a specific value. Because we have our calculator, kind of last class, we got to the idea of something really, really close to the left and something really, really close to the right and using those two values. But we didn't really do the calculations that say that equals a value. Well, let's actually find the value here by using our calculator's computational capabilities. That's an alliteration right there. Could be an English teacher.
In the graph function. We'll try.
All right, I was overhearing Mr. Patrick and Miss Robertson discussing, and they came up with great ideas. They said, you know what? And this could have been Mr. Schoonmaker helping out. A lot. Okay. Well, what they discussed is, hey, why don't we just use 2 points really, really close to 2? Why don't we talk about the x value at 1.99999 and the x value of 2.00001? So f of 2.00001, let's just use 4 zeros, minus f of 1. Let's use 4 nines. Now, here's the key. These are the function values. You can plug those into your function and get exact y values. Okay? So why don't everybody do that? Plug into your home screen. You don't need to be in your y equals. I see a lot of people going to the graph. You don't need to be in the graph. You need to be in your home screen, and you need to be able to plug in this value into this expression to get your y value. And you subtract this x value plugged into this expression to get your other y value. And then using your calculator, you can subtract those two y values and then divide by those two x values subtracted together. Now, I'll tell you, we're going to have something close to 0 and something close to 0 here, right? But we know when we have that, it doesn't mean that the value doesn't exist. This could be a number. Well, we're going to find that number. Beautiful. Awesome. Fantastic. Try again. Wonderful. Excellent. Check your value that you got with a neighbor's value that they got. Try again. I see a lot of people with the right answer. Some people are still struggling. Let's just make sure we're doing it the right way, because it's just good to see things. I got 3 times 2 point. I got only 4 zeros. 1, 2, 3, 4. I have to be very specific with how many zeros. I'm not just going to use random numbers here. I'm going to pick a number. I'm just going to stay with it. That could be the mistake that some people are making. Okay, minus 2. I'm going to subtract 1.999 plugged in. 4 nines, 9999 squared minus 2. Okay, that's my numerator, close to 0. I'm going to divide that by 2.00001, which is my x value, minus 1.1234 and I get a value very, very close to 12. Now, if I plugged in more zeros and more 9s, but kept them consistent, would this value probably get closer and closer to 12? Yeah. Some people, their calculator, they used more zeros and more 9s, and they got 12, which is your calculator just rounding because it got far enough away. They had enough zeros followed by a number that it just gave 12. Now, your calculator probably should say that we were approaching 12. We're getting really, really close to 12. But again, when we get really, really close to things, we essentially say that we are located at that value. Just like we say, if we have 1 over infinity, that's essentially 0, even though you know it has some value. It's really approaching 0, right? So this slope is 12. Questions about that?
I was just wondering if you can do it on the graph, with the y.
We'll worry about that later. Okay, we're just going to stick with this right now. Okay, good. So we have that. Now, let's kind of examine this function 3x squared minus 2 a little bit more. Because if I were looking at other locations, like what if I asked you to find the slope here at -1? What about the slope here at 0? What about the slope here at 1? We'd have to do that a bunch of times, right? And that would get tedious. We'd have to use our calculator at all times. And, we're not allowed to use our calculator at all times. So we need some other way to be able to find those slope values. Well, we'll lead you into this. We are going to sketch some tangent slope values. And hopefully this will help us understand kind of the next step that we need to take to be able to find these tangent slope values maybe in a quicker way. So I have this function. This is that function 3x squared minus 2. What I'm going to do is sketch some tangent slope values. Now, how are we going to do this? Well, there's a couple things that are very, very important when we're doing this. We have to understand slopes of lines. If I have a line that is very, very steep and going down from left to right, I would say that slope is, very negative, right? If I have a line that is a little shallower, we would say the slope is still negative, but it's a little less negative, right? I don't know exactly what it is, but it is less negative than the previous one. If I have a horizontal line, what is the slope of that line? 0. If I have a shallow line that is going up from left to right, we would say this is a little bit positive. If I had a steep line going up from left to right, we would say that's more and more positive, right? Well, what I'm going to do is I'm going to take this function, 3x squared minus 2, and I'm going to sketch little tangent slopes at specific points. Like at -2, at this point here, let's sketch a little tangent slope. Okay. Now this is a steep negative line, right? So what I'm going to do over here is I'm going to plot an approximation for that tangent slope value. Positives being above the x-axis, negatives being below the x-axis. So very negative, I'm going to go when x is -2 and plot a point that is very negative. Okay. You guys do the other 4 points. When x is -1, sketch a little tangent line, plot the approximation of that tangent slope. Think about it relative to the previous one. At 0, when x is 0, sketch the tangent slope, plot its value, then this value, this value. And look at your neighbors and see if you get the same things. No, you're good. Good.
Well, like the guy who's made calculus to the inside too.
Okay, so here we are less negative, right? So when x is -1, I'm less negative than the previous one. At 0, I have this what looks like a horizontal line, so I would plot the point, the tangent slope value of 0. At 1, I'm a little bit positive, and then at 2, I'm more positive. So I'm going here, I'm going here. So I just plotted some tangent slope values. Well, what does it look like we need to do with this situation? Some people did it. You did it, Mr. Brissett. You did it, Mr. Stockton. What did you do? Drew a line, right? It just kind of makes sense to draw a line right there, right? We got a bunch of points that look like right in a row. Why don't we just draw a line? Well, can we do that? Let's check. Well, this value right here, is that going to be a little bit less negative than this, but more negative than that? Oh, yeah, sure. That might fall right there. I looked at this value here. We're going to be shallower than this, but not quite at 0. So, yeah, so this is very, very interesting. Okay. What we can see from this kind of activity is that the tangent slope values to this function create its own function. Okay, so all of a sudden, maybe instead of worrying about looking at each individual location, which will take us a long time, maybe we can discover a function, okay, some equation, that the equation will tell us every single tangent slope value to here, okay? We know this is going to be some, y equals mx plus b. It's really mx plus 0, right? Well, now we are going to find those functions, okay? There are going to be functions that are going to tell us tangent slope values here. Let me show you. Let's do a different one. What if we had a function that looked like this? This is some x cubed. Why don't you sketch some tangent slope values and then connect them to make a tangent slope function? Check your answers with a neighbor for that one. What do we get? Again, we have 5 points. All we need to do is sketch my little tangent slopes and then understand the values, positive, negative, 0, more positive, more negative, less negative, and we'd be able to perhaps have something that we can connect, which instead of having just some random values plotted, we'd have a function. So I got a 0 here, and I got a 0 here. And I know this is positive, so I should be going 0, positive, 0, negative. So we'll do a couple more, that way we can practice. We should have at -2, this is the tangent slope, it is negative. At -1, the tangent slope is 0. At 0, the tangent slope is positive. At 1, the tangent slope is 0. At 2, the tangent slope is negative. Now, it looks like maybe we have possibly some kind of parabola. Maybe it's straight lines, I don't know. But it looks like a function, right? If I checked in between any two of these points, like at -0.5, am I going to have a positive slope? Well, at -0.5, I have a positive tangent slope. So that fits in right there. If I look at 0.5, am I going to have a less positive tangent slope? At 0.5, I have a less positive tangent slope. So it works out. So it's actually some sort of equation, some sort of x squared probably is going to give me the tangent slopes to all of these. Let's try one more. Let's try a challenge one. And this is 1. This is 2. This is 0. This is -1, -2. So it's a vertical asymptote. So this is really getting closer and closer and closer to this asymptote, and it's going to get, further and further up. It's never going to cross. It's just going to keep getting steeper and steeper and steeper. As well as this, it's going to get steeper, steeper, steeper down. What should you do? You should just sketch some tangent slopes on your function and then plot the values. This is my recommendation. Right here, tangent slope. Right here, tangent slope. Here, here. Compare those values and plot them. Here, tangent slope. Here, tangent slope. Here, here. Look at those values of those slopes and plot those values. Nice, Mr. Johnson. First one that I've seen has gotten it. This is a challenge one. I purposely, that's good, Miss Robertson. That's the right idea, Miss Nagel. All right, Mr. Johnson, what does your kind of tangent slope graph look like?
We go down like together.
So we start negative and we get more and more negative as I get closer to 1, right? So we kind of go down because we have negative slopes and they're continuously negative. How did I do that? Negative, more negative, even more negative. If we go further down, it's going to be more negative. Further down, more negative. But then I go and I skip over this asymptote where there's no point, and I go up here and I say, oh, well, this is a really negative slope as well. So I actually start back up with a really negative slope. And then it's less negative, less negative, less negative, less negative. We get something that looks like this. That will also have an asymptote because there's no function value there, so we can't have a slope. All right. Again, this is a function. This is some sort of function. This function, if I look at any point on this function, it'll tell me the tangent slope here. Our next step is trying to discover how we can find these functions. How can we find these kind of equations? Okay. And we are going to develop a magic formula that will be able to tell us the tangent slope function to any function. And it will be able to tell us the tangent slope values then for any function at any point. Okay? And we're going to start with just a random function, f of x. This is any function. And we will say this magic formula should work for any x value. So our goal is to generate some magical formula that will tell us the tangent slope to any function at x, any point. Well, to find a tangent slope, we have to understand that all it is just taking 2 points really, really close together, right? There's nothing more than that. I'm not changing that idea about 2 points infinitely close together. Now, what we did on the previous problem is we took a point right to the left of x and a point right to the right of x. We said x to the left and x to the right. Well, I'm going to make it easier. Because instead of going x to the left and x on the right, it's actually going to be the same as if I just look at x and x to the right. I'm just going to look at my specific location and right there. Is the exact same, essentially, as a point to the left and point to the right if I just take the location that I'm worried about and a point right to the right. It's 2 points still infinitely close together. Okay, it does not have to be on one side and the other side. Okay, so what I'm going to do is eventually take this point right here and move this point to be infinitely close to the right of this x. Okay, and it'll just be like going right and left. Now, this point I will designate as being at a distance away from x, some h distance. I'm going to add an h, just a value, and this point over here is x plus h. Okay? Giving me my second point right there. Now, I have the function values there. For this would be f of x, and this would be f of x plus h. Now, remember, all this is slope formulas, right? Slope. Well, I can start with the formula for the slope that I'm used to. F of b minus f of a over b minus a. But instead of using f of a and f of b, I have these things, okay? So I'm going to say this is f of b up here. That makes this b. And this is going to be f of a down here. That makes this a. Okay, so all of a sudden I'm just going to rewrite my regular slope formula for the slope of a secant line, but using x plus h and x. So let's do that. Slope of this secant line is f of x plus h minus f of x divided by x plus h, which is b, minus x, which is a. Okay? And right now, this is just the slope of my secant, slope of the secant. You know, 2 points, h distance apart. Well, is there something you can see in the denominator here? Yes, I have x plus h minus x. I can get rid of the x's. So all of a sudden, the slope of the secant is simply f of x plus h minus f of x all over h. All right, now this is the secant. What do I do to make this formula no longer a slope of a secant, but a slope of a tangent? So we talked about it. I have to take this point and put it really, really, really close to that point, right? Which means I need to take this x value and move it all the way over here. What do I do in this equation here to make that happen? We said h. Well, what happens to h? We have h as being some sort of, why isn't it? Some sort of value, right? And then as these points get closer and closer together, what is happening to h? It's getting smaller and smaller and smaller, right? Until h is infinitely small. Essentially 0. Can it be 0 though, Miss Lowy? It can't be 0, and why? Because you can't have 2 points on top of each other. It won't make a line. If you have 2 points on top of each other, you just have a point. It's not a line. I need 2 points infinitely close together. So I can't make h 0, but I'm going to have h get infinitely close to 0. What is that concept of getting something infinitely close to something? A limit. We're not talking about the exact value. We're talking about a limit as x is going to approach some value. So watch what I do. All I have to do is say the slope is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is the slope of a secant. This is the slope of a secant. This is now the slope of a tangent. This is the definition of a derivative of a function. This is my magical formula. that will generate tangent slope functions. That I can use to find any tangent slope value of any function. Or to use to find tangent slope values anywhere. This is just the slope of 2 points infinitely close together. But it'll give us this. Okay, it's just a slope formula. Now there's an alternate way that I could have generated this magical formula. I could have talked about 2 points, f of x and f of a. And I'll have the 2 y's subtracted from each other. And the 2 x's subtracted from each other. And I'd be looking at the actual value at A, the tangent slope at A. So what I would do is actually take x and make it really, really close to A. And this, instead of giving you a tangent slope function, this will actually just give you a specific tangent slope. This is exactly kind of what we did when we used our calculator. This can be thought of as an alternate definition of a derivative. Or an alternate formula. This is the tangent slope at A. But I want the tangent slope at x. I want a function that can give me anything, so we usually use the one on the top. Okay? Now, some notation. We have f of x being the function that we're looking at. For example, 3x squared minus 2. We will find the tangent slope generating function, and we will call it f prime of x. This little tick mark right here, we say is prime. It's just a little tick mark. And this will equal something, and we're going to find out in a second. It's going to equal some function. Okay? This f prime of x will be the tangent slope generating function. So actually, when we were doing all those graphs, we started out with an f of x. We actually graphed f prime of x. We are graphing what we call this derivative function. We are graphing what we think the tangent slope generating function is going to be. We think if I have some x cubed, its tangent slope generator is going to be some kind of x squared. It's going to be very specific. We'll be able to find the specific function for it. For 3x squared minus 2, we think the derivative f prime is going to be some y equals mx plus 0. But we need to find exactly what it is, okay? So let's go ahead and do it. Let's find the tangent slope generator for 3x squared minus 2. Okay, how are we going to find it? Well, we are going to use our magic formula. Okay. Now we say this magic formula will give us f prime of x. So maybe that's something to add. Instead of slopes of tangents here, you can say this magic slope formula gives us f prime of x. Okay, now what we're going to do is we're going to need to plug in f of x here. Now we also need f of x plus h plugged in here. I need to figure out what f of x plus h is. Well, it's easy. Instead of plugging in x, wherever you see x, use x plus h. So it's 3x plus h squared minus 2. Okay. Well, that gets plugged in here. Okay. Let's go ahead and do that. And the limit as h approaches 0 of 3 times x plus h squared minus 2 minus, now it's important, we're subtracting this entire f of x. If you need to put that in parentheses to remember that, do that, because I need to subtract this entire 3x squared minus 2. This is all going to be over h. Cool, right? Well, we have a limit. First attempt is to find the function value. If this has a value, I plug in 0 for h. What do I get? 0 over 0, right? Undefined. We know if we have 0 over 0, though, that doesn't mean the limit doesn't exist. It could equal a number. Usually equals a number. What do we have to do then? Distribute, simplify. All of these techniques we learned from the first units are coming back to us so that we can handle this magic formula. So let's go ahead and do that. I'm going to distribute the x plus h squared. Distribute this negative. This would be minus 3x squared plus 2. All over h. Then I'll distribute the 3 everywhere. Now the magic happens. Some stuff cancels. 3x squared minus 3x squared. Positive 2, negative 2. Leaving me with 6xh plus 3h squared. What do they both share? They both share an h. Pull out the h. Cancel the h's. What do we get? Well, I just have to find the limit as h approaches 0 of 6x plus 3h. Don't forget the last step. Plug in 0 for h. What do we get? 6x. This is f prime. This is that equation that I graphed at the beginning of class. This here that we just kind of sketched, this is a specific function. This is 6x. what does this mean? This means I can plug in any value into 6x, and this will tell me the tangent slope to 3x squared minus 2 anywhere. So, if you want to find the derivative, which is the same as the slope of the tangent, which is the same as the instantaneous rate of change, of this function when x equals 3, guess what? You have something that can tell you the derivative or the tangent slope to that function anywhere. We just need to plug in 3. What was the value that we looked at? Did we look at 3 earlier? We looked at 2. So this would have made sense if this was 2. Let's go back to this and say, what is the tangent slope when x is 2? Well, look at this. If I plug in 2, I got that same value that I found using my calculator, 12. Only now that I have this function, I can tell you that value at 2, as well as any tangent slope value anywhere on this. Okay? Now, some key things to remember. If I have a function, this function will give you points if I plug in. If I have a tangent slope generator, you plug in values in here, you'll get tangent slopes of the original function. This is my helper equation. Sorry, plug in x, you'll get points on f of x. Plug in x, you'll get slopes of f of x. So I could ask you this. What is the equation of the line tangent to 3x squared minus 2 at 1 or at 3? What are the two things you need for a line? Slope and a point, right? Make sure you write down this question. Because we will be finding lots of equations of tangent lines. So I need a slope and a point. Well, it's not just any slope, it's going to be a tangent slope. Where do tangents come from? Tangent slopes come from? Comes from this derivative function. Where are the points going to come from? It's going to come from my original function. Why don't we do it at x equals 2 and x equals 3? Yeah, sure. Now, we already know what the tangent slope is at 2. We found it numerically and using my magical formula. It's 12. Well, now we just need a point. Plug in 2 into my original function. 4 times 3 is 12. 12 minus 2 is 10. That information will give me my equation. Y minus 10 is equal to 12, x minus 2. Now, it's all fun and games when we're just finding things. But it helps if we can see that this is true. And this is where, you know, this is great. Because we have calculators that can graph this and graph this. And we should be able to see that this line is tangent to this at 2. So this comes the beautiful part of this class when we can graph this. Now, an easy way to solve for y is just to add this 10 on the end. Of course, you can distribute the 12, but if this was a different value, like a fraction, you don't want to distribute and add. So just add the 10 at the end. But this is the beautiful part in the class where you're going to graph this in your calculator. You're going to graph this in your calculator. And you're going to be able to see this is a line that will just touch this function at that one location. Isn't that beautiful? I think so. Well, go ahead and find the equation of the line tangent to this function at x equals -1. And once you find the equation, go ahead and graph that one as well, so that you have a function and two tangent lines at two locations. What are you going to need? You're going to need the tangent slope of this function at -1. Well, it's a good thing we have that helper function, that f prime function. It's going to tell us the tangent slope values everywhere. That will help us. That will give us the tangent slope. And then the second thing you need is the point on the function when x is -1. Go ahead and find that and check your answers with a neighbor. But also check your answers by graphing. And when you graph, you should be able to see the function and its tangent. Beautiful. Do it at -1, not at 3. Y minus y1. Yeah, so for your equation of the line, y minus y1 equals m times x minus x1. Good, check. See if that's correct. I would say this 2 is not going to be right? Because this is the point, this is your x, this is your y, so this is -1 here. So x minus -1, right? So this 2 came from the fact that I'm talking about f of 2 being equal to 10 to 10. If I change my point, I'm going to change my equation, right? So let's find f of -1. I plug in -1, I get 3 minus 2, which is 1. So here's my point, -1, 1. So that means I have y minus 1 equals some slope x plus 1, right? Now, what's the slope? -6. How do we get that slope? Well, we already used my magical formula to find the tangent slope generator. And when I plug in -1 to that tangent slope generator, it gives me the tangent slope at that location. This is telling me not only the tangent slope, but the instantaneous rate of change of the function, which is telling me that at this location, my function is decreasing. It's going down 6 y units for every x unit. If you look at the graph of 3x squared minus 2, when x is -1, not there yet. Here, you can see that the graph is going down. At what rate? 6 y units per x unit. It's like an instantaneous velocity. It's like exactly what's going on at that moment. Okay? Cool. Well, let's find another tangent slope generator, and let's generate some more tangent slope lines. Well, let's just go over the procedure. And if we want to put the procedure at the top of the page or somewhere else so that you know, put it there. That way you just understand. Step 1 is to use your magic formula to find f prime, because this equals f prime. Second thing, once you find f prime, you use f prime to find tangent slopes. And don't forget to use f to find the point that you're looking for. And then combine those two things, you have your equations. So we want equation of a line tangent to root x plus 1 when x is 3. Sometimes it helps to kind of sketch the function and what its derivative function will look like. Root x plus 1 will look like this. Not a great graph. Look like that. This is f of x. Let's see, what would the tangent slopes look like? Well, it'd be very positive, less positive, less positive, less positive, less positive. So we'd be talking about positive, less positive, less positive, something like that. That would be f prime. Okay, let's figure out what that equation equals. All right. Well, I know what f of x is. F of x will go in here. Now I figure out what f of x plus h is. Wherever you have x, use x plus h. So instead of root x plus 1, it's root x plus h plus 1. Then I will plug that into my magic formula. Now we got root x plus h plus 1. That's x plus h minus root x plus 1 divided by h. Now if you wanted to, you could have plugged in 3 into this and just find it right away. But I like to have f prime of x. That way I can plug in any value. So I'm going to keep x in there. Now, what is this screaming for me to do? Conjugate, right? I see square roots. How do you get rid of those square roots? Multiply by the conjugate. Don't forget to multiply the top and bottom by the conjugate. Now we get x plus h plus 1 minus. Don't forget to put the quantity. Put stuff in parentheses or you will make mistakes. All divided by h times, don't forget what you're multiplying by, this. Distribute this negative. Negative x, negative 1. The x's will cancel, the 1's will cancel. Boom. boom, boom, boom. The h's will cancel. We just have an h over an h left over. They will cancel after all the other stuff cancels, giving me the limit as h approaches 0 of 1 over root x plus h plus 1 plus root x plus 1. Don't forget the last step of plugging in 0 for h, giving me 1 over root x plus 1, which is 1 over 2 root x plus 1. This is f prime. Graph it in your calculator. You'll see something that looks like this. I'm going to graph it. One over 2 root x plus 1. There we go. Just like I thought. Now I'd have to zoom in to see it, but it's looking just like this, right? Okay, but that's not what I'm here for. I'm here for specifically the equation of the line tangent to this function when x equals 3. So for that, I need a tangent slope at x equals 3. We're just going to finish off this problem. I get 1 over 2 root 4. This is f prime of 3, which is 1/4. I need a point. A point comes from the original function. That's f of 3, which is root 3 plus 1, root 4, which is 2. Giving me my equation. Y minus 2 is equal to 1/4 x minus 3. You can graph this and graph this, and you'd be able to see this being tangent to that at 3. Now, there's one more example that I'm going to show you in the video, and I'm going to actually do it right now because I'm recording, that you do not have to listen to. You can start your study hall, but I'm going to do it regardless. And if you have someplace to go, you go there. Okay? There's one more thing you guys should hear, though, is situations when we can't have derivatives. Well, functions must be continuous. You can't have a derivative at a jump or an asymptote or a hole. And you can't have any sharp points. A situation like this, we don't have a derivative at this location. There's no tangent slope at that location. Who could tell me why? No, I could have something like this. We would say the slope is undefined there, but why? At this sharp point, we don't have a derivative. Well, if you think about it, we're talking about a limit. It's the limit as, this approaches 0 of this, x plus h minus f of x. Sorry for being messy. Right? For limits to exist, the left-hand limit has to equal the right-hand limit. That means the slopes from the left have to approach the same value as the slopes from the right. These slopes from the left are all negative, and they're not decreasing. They're just negative. These slopes from the right are all positive, and they're not decreasing. They're all positive. That's why at a sharp point, we say there is no tangent slope. Okay? At a vertical asymptote, no tangent slope. You don't even have a point. At a hole, we don't have a point. We don't have a tangent slope. At a jump, we don't have a tangent slope. And at sharp points, we don't have tangent slopes. Okay? All right. Start study hall right now. I'm going to do the last problem. If you are not doing anything, you might as well just write down this last problem, where we're going to remind ourselves of how to use common denominators to handle those big limits. So I'm going to find the equation of the line tangent to this function at 2 over x plus 3 when x is 1. Step 1, magic formula to find f prime. Make sure we know what f of x plus h is. F of x goes in there. I'm going to write down f of x plus h being 2 over x plus h plus 3. That gets plugged in there. F of x gets plugged in there. Let's go. Whenever you see fractions inside of fractions, you should be screaming at yourself to use a common denominator. Now, a common denominator is typically the product of the two denominators. Multiply this by x plus 3, x plus 3. Multiply this by x plus h plus 3, x plus h plus 3. Be careful, you are subtracting this entire thing. So keep those parentheses handy, because you're going to make mistakes if you don't use parentheses. We get 2x plus 3. You can distribute the 2. It might go quicker that way. Minus the quantity of 2 times x plus h plus 3. All being divided by the common denominator, x plus 3 times x plus h plus 3. Then that's all being divided by h. But remember, when we're dividing by h, that's like multiplying by 1 over h. So I really just have an h over here somewhere. Well, now let's go ahead and distribute. Distribute the negative as well. This is like a negative 2 being distributed. So it's distributing that negative symbol. You get 2x plus 6 plus negative 2x plus negative 2h plus negative 6. All being divided by x plus 3 times x plus h plus 3 times h. I just move the h next to here. You can do that. Okay, this is all stuff we've done before. This process is not new, but it's good to practice. 2 x's, gone. 6's, gone. What do we have? A negative 2h over h left over. Well, if you have negative 2h over this entire denominator, the h's will cancel, leaving you with the limit as h approaches 0 of just negative 2 over x plus 3, x plus h plus 3. Okay, that's all simplification. And don't forget the final step, plug in 0 for h, giving me my tangent slope generator, x plus 3 squared. Negative 2 over x plus 3 squared. Now, actually, if you graph negative 2 over x plus 3 squared, you would see that it would look just like this function here. This is just like our original function. This is what that derivative looks like. We already sketched it, Now we just found the actual equation for it. It's fascinating. So now if I plug in any x, I'd find any tangent slope to this original function. Well, we're asked to find specifically the equation for the line when x is 1 to this. Well, let's find my point and my slope. We use f of x to find my point. F of 1 is just going to be, this is point, 2 over 1 plus 3, which is 2/4, which is 1/2. And then I can find my slope, my tangent slope. My tangent slope, my instantaneous rate of change, will come from f prime here. -2 over x plus 3 squared. It's my tangent slope generator. I find it at 1, f prime of 1. -2 over 1 plus 3 squared. Right? Yep. So 4 squared is 16. Under 2, this is -1/8 after you simplify. There's my slope. Here's my point, 1, 1/2. I get y minus 1/2 equals -1/8 x minus 1. Now for fun, I'm going to graph this and that and make sure that this is tangent to this there. Y equals 2 over the quantity of x plus 3. And y equals, I'll just add the half at the end. Again, that's helpful. Instead of distributing the 1/8 and everything. -1/8 x minus 1 plus 1/2. There's that original function. And here comes my tangent line. If you zoom in closer to 1, you'd be able to see it even clearer. There's 1. Here comes my tangent line. Bloop, right there. Good stuff. Calculus.